Welcome to another Ocean Ideas Talk, brought to you by ocean lovers.
Now, I am delighted to introduce our next panel session. Very excited about this one. This is about, can our reefs save themselves? And we have three extraordinary experts in this field to share with you today. We're going to be hearing from leading researchers as they discuss the survival strategies and the evolutionary traits that help reefs survive during ongoing climate change and rapid heating events, and conversely, how science and conservation need to intervene to help protect them. Please would you join me in welcoming Dr. Elliot Scanes, Dr. Emma Kemp, and Dr. Cheng Chen. Very quick bios. Dr. Elliot Scanes is an ARC Discovery Early Research Fellow in the Climate Change Cluster at UTS. He's a marine biologist and ecologist who focuses on understanding how marine organisms will respond to climate change. Dr. Emma Kemp is a marine biologist and team leader of the Future Reefs team at UTS. Her research ranges from organism-scale molecular signatures to broad-scale ecological interactions. And Dr. Cheng Chen is an engineering postdoc fellow at SIMS, the Sydney Institute of Marine Science, who works primarily on the cooling and shading sub-program of the Reef Restoration and Adaptation Program, the world's largest initiative dedicated to protecting the Great Barrier Reef. Now, we're going to hear a little bit more from each of them about their work, starting maybe over on that side with Emma, and then there will be a chance for questions from the floor as well. Emma, tell us a bit more about what you do saving the reefs in particular.
So I lead a team at UTS called the Future Reefs team, and we are looking at cellular level biology all the way through to ecosystem restoration to try and understand how reefs may survive ongoing climate change. Really topical issue. We're currently in the 5th mass coral bleaching event on the Great Barrier Reef in the past 8 years. The current bleaching event is spreading all the way from the south, so from Heron Island all the way to the Northern Reef. So we know that if we don't address climate change, we're unlikely to have reefs, at least as we know them, in our lifetime. But we need to buy time for reefs. And so there's a toolbox of approaches. We're going to hear about some of them here today. So our team's really interested in naturally tolerant corals within just reef systems. So we try to identify these corals through something called phenotyping. So basically looking for traits that make corals more tolerant to heat. We try to find them, try to grow them up on nurseries and put them back on the reef. But this is local scale, and obviously the reef's the size of Italy, and so we've got a lot we still need to do.
Yeah. Now, Elliot, your work focuses on how marine organisms respond to climate change. Tell us a bit more about what you do and about your work with the reefs.
So when we when we think about reefs, we know that the Great Barrier Reef and coral reefs are really famous and beautiful example. However, there's lots of other types of reefs throughout Australia, namely temperate rocky reefs and also oyster reefs, which are a really important element of our estuaries and coastal environments. So my work focuses a lot on oysters and their biology, how they interact with their environment, and at UTS, what we do is mostly research the bacterial interactions with oysters. How is climate change potentially making them sick and affecting the oysters in our estuaries that are so important for creating habitat for fish and cleaning the waterways, but also a food source for people. We all love, a lot of people do love to eat them. So is that also an issue with climate change? So we work, like Emma, from the very small bacterial level all the way up to the whole oyster, trying to understand how those interactions are being altered by climate change.
So start one off for a layman like me. How do oysters interact with their environment?
Well, they can't move, but they can sense their environment through a range of mechanisms. They sense vibrations, they know when to shut their shell for protection, but also they filter the water that's around them. So that's when we talk about cleaning the water. They take in the water, they take out all the particulates, they keep what they think is a good source of food, so little organisms, or be it algae, keep that for food, and they, instead of putting the stuff that they don't want back into the water column, they actually deposit it on the bottom of the waterway. So in that way, they clean the system. So they're really important for interacting in that respect.
Now, Cheng, I know you work on the cooling and shading of the reef. Emma has told us this is the size of Italy. How do you cool and shade something the size of Italy?
So basically, for me, I'm actually an engineer. So being surrounded by marine scientists every day, I learn so much. So basically, I'm working on a very interesting and exciting project called Cooling and Shading Subprogram of Reef Restoration Adaptation Program. So what we essentially are developing is a technology called marine cloud brightening. So basically, it's a process of making larger and more reflective cloud over the ocean, so we can potentially cool and shade the reef, potentially reduce the water temperature, so we can sort of help relieve the stress from the coral.
So marine cloud brightening. How do we do that?
So basically, so think about a scenario where, like, I woke up sort of in the morning on a large research vessel. We've got a 20-foot shipping container worth of scientific gears. We've got air compressors, high pressure water pumps. Basically, by utilizing nozzle atomization technology, we can atomize, we pump the seawater and filter it and atomize it into nanoparticle size sea salt aerosols. Particles. As the sea salt particles rise up, we have a big, huge fan at the back, push it up. So as it dissipates, it arrives to a low-lying cloud, sort of around 500 to 1,000 meters high. So by injecting more sea salt aerosols, we can make the clouds brighter, so it can deflect more sunlight back to the atmosphere. So the ultimate aim is to potentially reduce the water temperature.
And how do we do this at scale? Because obviously, I mean, we can do this with the nozzles and the aerosols, but how do we do this over a larger and larger area?
Yeah, definitely. So our group, we started from 4 years ago, starting from investigating a single nozzle, how many particles we can produce. And now from one, we've already up to the third version of our prototype. So we are able to produce like 100 trillions of particles from 30 ml of a shot glass of water. So we probably from the video you probably can see from YouTube, or there's even a documentary about our work. It's called Optimist Guide to the Planet, filmed by a famous guy, Nicola, who's the guy, Game of Thrones, James Lannister, probably you heard of him. So for that documentary, you should be able to find out the scope of our work. So to answer your question, so my supervisor, Professor Daniel Harrison, he's envisioned to have 800 stations across the whole reef to be able to cover the whole reef. But we currently starting from the high value reef and the most bleached reef to start with.
That sounds amazing, certainly from the engineering, the scientific perspective. Emma, what role do communities play in this restoration? I know there's extraordinary science and marine biologists working away. What role do communities play?
Yeah, it's a great question, absolutely fundamental. Reefs are considered socio-ecological systems, so they're absolutely, communities around the world fundamentally rely on reefs. Many of the poorest communities, the ones that have the least social license to do anything about climate change, but are actually the ones experiencing the impacts of climate change the most, fundamentally rely on reefs for their survival. So around the world, communities are getting involved in community restoration. It's local, it's high-value sites. It's definitely not operating at the size of the reef like we know that RRAP's doing. But ultimately, it's about bringing them on board. It's about social resilience. In 2021, the United Nations made it an emergent human right to a healthy environment and nature. It's not a human right yet, but it's an emergent right. And that shows that we have to bring people with us on this journey. And so in Australia, we have traditional owner groups and also local communities such as tourism operators working to integrate restoration practices, but looking forward also forming a community of practitioners that, as people like RAP at the Australian Institute of Marine Science get more solutions that we can try to put into place, the community is there, they've been on board, and they can be brought with us as we put those into play.
Gotcha. I know you co-founded the Coral Nurture Program. Can you tell us a little bit about that and how it fits in with the broader restoration efforts?
So 2016 and 2017 was the first back-to-back coral bleaching events here on the Great Barrier Reef. And that was a real sort of pivot for marine conservation, at least with reefs in Australia. Before that, there was no restoration efforts happening. RAP didn't exist. There was no restoration efforts happening. But about 30% of the reef was lost during that back-to-back bleaching event. And the community, particularly the tourism industry, said we want to be able to do something. They could already do site stewardship, so they could remove things like crown of thorns, which are invasive and can eat a lot of the coral. But they wanted to be involved in restoration. And so with some traditional owner groups and with the tourism industry, we set up nurseries to really ask how science can inform practice for restoration, but also how community knowledge can feed into that. So we've outplanted about 110,000 corals to date at high value sites on the reef. And all of that's been tracked scientifically. So we could see what did work, what didn't work, which sites are doing better than others. We have an experiment going on right now in the middle of the bleaching event to see why some species, why some sites are doing better. And hopefully as a community, we can share that knowledge for the reef.
Elliot, I think, certainly with me, I'm not going to speak for everyone in the room, but most of the time if you talk about reefs, people think about coral reefs, and Australia has, huge diversity of different types of reef. You mentioned oysters, but can you tell us a bit more about that diversity?
Certainly. So the Great Southern Reef, which is something we may not have heard of, is actually 8,000 kilometres longer and significantly bigger than the Great Barrier Reef. So the Great Southern Reef goes all the way from here in New South Wales, around Tasmania, and wraps up into Western Australia. It's comprised of rocky habitats, connected just like the Great Barrier Reef is little isolated pieces of coral. This is isolated rocky habitats colonised by things like kelp, which perform a lot of the services like providing habitat for the organisms that live on the Great Southern Reef. Similarly, unfortunately, it's also under pressure from climate change because kelps like cold water, and as more hot water comes down from north of Australia, especially on the eastern coast, and we enter these marine heatwave events like we're experiencing off the coast of Sydney right now, kelps, they cannot handle it, they also are dying, and that means a loss of habitat for lots of other organisms. So reefs in the temperate zone of Australia, so that is essentially everywhere south of Queensland, they are also really important for ocean, as we, the marine ecosystem. Even within Sydney Harbour, we have lots of isolated patches of rocky reefs, which are really important biodiversity hotspots for fish and other organisms.
So what's being done to save these different, the Great Southern Reef? What projects are underway to help save these different reefs?
So the Great Southern Reef, there's experts who can talk more about it than me, but certainly there's kelp restoration that's going on, just like we have coral reef restoration, whereby tolerant species of kelp, or perhaps those individuals that have shown to be resilient to warm water, are planted out, and this is going on the coast of Tasmania as we speak. So there's certainly active restoration efforts in that space. Similarly, as I talked about oysters before, oyster reef restoration is one of the biggest restoration projects ongoing in Australia at the moment as well. Australia used to have huge oyster beds within our estuaries, especially in Sydney Harbour. However, after the arrival of Europeans, they were really over-harvested, and over 98% of those reefs have actually been lost. So there's a lot of ongoing work to restore those reefs in addition. So they were lost through over-harvesting. However, factors like climate change and pollution are really preventing them from coming back. So when we restore these types of ecosystems, we need to also consider those factors that could affect their success.
Gotcha. Now, I'm just going to squeak in one last question to Cheng, and then I'm going to come to the audience for questions. Can you share with us maybe a few of your experiences from your most recent field trip to the Great Barrier Reef? What did you see? How's the work going?
So basically, I spend 4 weeks up on the reef, living on the boat. So every day we wake up sort of 7 o'clock in the morning, check the weather, and then check all the gears because we're running high pressure system. We're talking about 200 bar. So the high pressure big enough to, cause danger. So we sort of, and also, so we've got two large research vessels. So the vessel I'm working on is called a walkboat. So it's a creation of sea salt aerosols. There's another boat downstream that captures the aerosol we produce. Because we can't just, by using naked eye to see, okay, you are producing aerosols, it's going to work. No, we have to produce the right size and the right amount to be effective to affect the clouds. So there's another vessel downstream capture all these aerosols and measure the size and production rate. There's also an airplane, dedicated airplane fitted with 20 instruments. So the airplane fly through the clouds to measure whether the targeted clouds has been seeded or not. So it's a whole big amount of work we've been done. And last year was about 6 weeks. I was up on the reef, somewhere near Heron Island and One Tree Island. This year was with Sunday Island, somewhere near that. As I remember, Good Reef and Willoughby Reef. So that was some quality time we've spent over there. We've got enough data to support that we are actually brightening the clouds. Now it's just a lot more further research work. We need to optimize this technology.
Gotcha. Thank you. That sounds like an extraordinary undertaking, not just pumping the aerosols out, but then measuring it at sea, measuring it in the air.
I'm actually just representing our group, just one single person out of 50 of us. We've got a meteorologist tell us what the weather look like, and also a cloud specialist to tell us whether clouds has been seeded or not. A few guys working at QT doing atmospheric sampling. We've got a large drone pad on top of the 20-foot shipping container. They do daily atmospheric profile sort of thing to measure the humidity, temperature. That's all sorts of parameters. We are doing a lot of work. Yeah.
Do they let you fly the plane?
No. I wouldn't like to because it's 4 hours. You are not allowed to. You're just sitting there, watch the screen and click buttons.
I think we have a spare. We do. We have a microphone there and a question. Yes, lady in the aisle.
Hello, thank you. This was really great. My question I think is for Emma. So are you doing genetic research at all to look at the zooxanthellae and the holobian where there's, I guess I'm wondering if when you're genetically researching, are you looking for the coral or that algae zooxanthellae? And if you're looking for a more genetically resistant to climate change, would you say it's more important to look at the actual coral's genetics or the algae? Thank you.
Great question. So we look at both the holobiont, so the animal itself, and algae. We find that the type of algae that associates with coral is one of the big factors that determines the resilience, but also that the host genetics comes into play. So when we're working at a site and looking at restoration, we'll do the population genetics of the animal and see what it is. And that's really important to make sure that we're not kind of propagating lots of the same thing and we're keeping biodiversity because that's crucial for resilience. But we'll also look at the symbiotic algae. And there's other groups at the Australian Institute of Marine Science that are looking at how they can actually select certain types of algae and try to re-inoculate them into different animal hosts to boost resilience that way. So it's a bit of both.
That was a great question, by the way. Any other questions around the audience? Yes, there's 3 hands gone up, all on this side. Come on, this side. Come on, get your act together. One there, and then one forward.
I think for Dr. Scanes, please, Elliot. Reefs, we know coral reefs are basically because little organisms create them and they're mounds. But what about the Great Southern Reef? Is the rock formations actually raised up, or is it just defined by the amount of the algae growing on it? How do you define these other reefs?
Yeah, so that is again a great question because Coral reefs and oyster reefs would be classed what we call a biogenic reef. So that is essentially all the organisms living together have created that over hundreds and potentially thousands or millions of years. When we're talking about the Great Southern Reef, a lot of these interconnected reefs start by natural rock formations, so be it underwater rock formations from extinct volcanoes or just geographical features of the seabed, which is really what makes it quite unique, because in some ways the geology of southern Australia happens to be just right for the formation of this kind of reef. So then once we have the available habitat, like the rocky substrates that are there, we get colonisation from the animals that can live there, specifically the large kelps that form the habitat and then form the basis of the other for all the other organisms. So in a way, the kelps are kind of acting like the corals, but they need that rocky substrate to be there in the first place so that they can colonise and form the habitat that allows everything else to live there.
And there's a question just here as well.
I have two questions, one for Emma. What are those specific coral species you're finding in these hostile environments? And one for Cheng, do you think that that is a long-term solution? Or thank you.
Yeah, I think so. All the intervention strategies we are trying to develop and trying to push harder is to buy more time for the corals. So the ultimate solution is to cut the carbon emission. That's probably the only way we can reduce global warming, which is a killer for the corals.
And Emma, do you want to take the first part?
Yeah. And so different species, but we find in reef adjacent habitats, so things like mangroves, we find all different types of corals, and actually genetically they're the same as what we find on the reef, but they have different algae, and so we think that's part of the reason that they're more tolerant. So we've been moving them out of those systems to see how they go over the summer when we're seeing bleaching and do they survive. So it's been more the algae in that instance that's given them the tolerance.
Thank you. There was another question just... Oh, hand went straight up, just there.
Thank you very much for your awesome work. I'm just blown away by what you've been talking about. My question is, are scientists the most optimistic people in our society?
That's a good question. That was actually my last question on my sheet here. So we might wrap this up by saying, if not, are you the most optimistic? Like, are you hopeful for the outcomes of your work? Like, do you really think this will create that positive change in the long term? Emma, let's start with you and we'll work our way back.
So I just spent last week on the reef sites I've studied for the last 10 years, completely white from the impacts of climate change. And so I'm realistic. I think that reefs will not exist as we know them in our lifetime if we don't deal with climate change faster. No amount of science is going to get us there without that. But in saying that, there is, so many people around the world that are working on solutions. We still have amazing reefs that are worth fighting for. And for me, that's why I do remain optimistic, because we have reefs there. Reefs have shown us that they're really resilient. That many sites recovered from the 2016-2017 bleaching event because they had time. We've just got to get we've got to get the action to give them that time, but also get science and innovation, engineering to also help buy that time. So cautioned optimism from me.
And Elliot, are you also a cautious optimist?
Yes, well, it is difficult to be optimistic when we're the ones at the coalface sort of understanding, all of the impacts and having, that intimate knowledge of just what our organisms and our ecosystems are up against. However, we know that life on Earth is resilient, and Emma's mentioned how resilient coral reefs are. They've existed for however many millions of years. And we know that our other types of reefs are similarly resilient. So I do have optimism that within these reefs there is the potential to continue to persist for future generations. So while it can be difficult to be optimistic, yes, while I guess I get to see both sides of the coin, in that we can see that they're under pressure and there's lots of threats. However, every day we get to see how special, how resilient these organisms actually are, and that does give me optimism going forward.
Thank you, and Cheng.
I think I'm optimistic as well. Before I start this job, my boss, my supervisor, Dan Harrison, was asking me, "Hey Chen, we've got a single nozzle working now. It's producing this much of aerosol, and now we've got a first prototype having 100 nozzles. Is gonna work. And can you make 1,000 nozzles to be able to work, produce the right amount of aerosol to be effective for us to carry out the airplane experiment?" I'm like, yes. And 2 years now we made it. So I think we just have to try our best to make things happen. That's probably what the scientists want to do, to discover what we can do, what we cannot do, because we can't just wait till coral completely die, because according to the model I recently read, by the year of 2050, if the seawater temperature goes up by 2%, 90% of the coral is gonna die. So we don't want that to happen. That's why we try so desperately to push all the technology to be able to deploy, to increase their technological readiness, so we can just roll out and make it happen on the reef.
So realistic optimism, I think, is where we will need to leave this. Please would you join me in thanking Emma, Elliot and Cheng.
Thanks for tuning in. We hope you enjoyed this episode of Ocean Ideas. Please make sure to share it with your networks and help us in our mission to turn ripples of action into waves of change for our blue planet.